A very good morning and namaskaram to all. Honorable guests, faculty members, participants and my dear friends. Myself, Shikha Saxena, a PhD scholar in the Department of Mathematics and Computing at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. I, on the behalf of NTIJ family, extended a warm welcome to all the distinguished dignitaries, respected guests, and enthusiastic participants for the inaugural ceremony of GIAN course. It is one of the greatest initiatives taken by the Government of India in the education sector. With the special thanks to the Ministry of Human Resources and Development, NIT Jalandhar is privileged to host the inaugural ceremony of GIAN course on Dynamical System and Chaos Theory, Internet of Things and Cryptography application. I take the great pride in welcoming our Honorable Director, Professor B.K. Kanojia. We are highly honored with your presence, sir. We are delighted to extend a hearty welcome to our esteemed experts of this GIAN course, Professor Dr. Lombardo Rondoni from Politecnico di Torino, Italy, and Dr. Noor Aisha Abdul Fattah from National Defense University of Malaysia. We are deeply grateful to you, sir and ma'am, for accepting our invitation and gracing this event with your presence. Thank you. We have with us Dr. Raghav Ramansina, Head of the Department of Mathematics and Computing, Local Course Coordinator Dr. N.K. Srivastava, and Course Coordinator of this program Dr. R. Shivraj. Now, I would like to call upon the dignitaries to kindly come forward for our traditional auspicious lamp lighting ceremony. This lamp lighting ceremony is a tribute to Mother Saraswati, the goddess of knowledge. Please come forward.
से सारे अपडेट्स पाने के लिए बेल आइकन दबाएं।
GIAN. If we consider this as a Hindi word, it means knowledge. Here, I would like to quote a beautiful quotation by Mr. Kofi Annan, Knowledge is power. Information is liberating. Education is the premise of progress in every society, in every family. At this moment, I would like to request Dr. R. Shivraj, the course coordinator of the GIAN course, to deliver the welcome address and also shed the light on the objective of this course. Sir.
Very good morning to all. Very good morning to very good morning to everyone. So, on behalf of the Department of Mathematics and Computing, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, it gives immense pleasure and honor to extend a warm welcome to all the distinguished dignitaries, esteemed guests, enthusiastic participants for the inaugural ceremony of the Global Initiative on Academic Network, known as GIAN, course on Dynamical Systems and Chaos Theory, IoT and Cryptography applications, organized during January 6 to 11, 2025. This GIAN is one of the schemes funded by the Ministry of Education. I am Dr. R. Sivaraj, and as a representative of the department, I take great pride in welcoming our esteemed chief guest, most respected Professor Binod Kumar Kanajia, Director, Dr. B.R. Ambedkar, NIT Jalandhar. Sir, we welcome you, sir. We delighted to extend a hearty welcome to our esteemed guest of honor, Professor Lamberto Rondani from Politecnico di Torino, Italy. We welcome you, sir. We extend our warm welcome to our another speaker, Dr. Noor Aisa Abdul Fatah from National Defense University of Malaya. We welcome you, Professor. We are deeply grateful to both of you for accepting our invitation and gracing this event instead of your very tight schedule. It's a great privilege to welcome Dr. Raghav Raman Sinha, Head, Department of Mathematics and Computing, Dr. B.R. Ambedkar National Institute of Technology. Welcome you, sir. We are delighted to extend a hearty welcome to the local course coordinator, Dr. N.K. Srivastava from Department of Chemical Engineering, Dr. B.R. Ambedkar NIT Jalandhar. Welcome you, sir. It's my pleasure to welcome all the deans and HODs and of the various departments of our NIT Jalandhar to the inaugural ceremony of the GIAN course. I extend my wholehearted welcome to all our participants, those who come from 13 different states of India, covering from Tamil Nadu to Kashmir. And I really feel that it is one of the very important thing that whatever the program we organize, the participants, enthusiastic participants, we are having here 43 participants, almost from 13 different states of India. We welcome you all on behalf of the Department of Mathematics and the GIAN course. The dynamical systems deal with the evaluation of time-dependent systems. So we know very well that modeling is one of the very important thing in mathematics. This serves to all the engineering, science, and technological process. In mathematical modeling, the systems depending to the initial conditions is one of the most important thing. So the chaos theory as well as the dynamical systems deal with the systems which are so important, that is giving most importance to the changes in the initial conditions. So we are having here the eminent speakers, and they have served for more than decades in this field, like Professor Lamberto Rondani and Dr. Noor Aisa Fatah. From their experience, we are going to have the course being taught in 12 lecture hours and 5 tutorial hours. In this particularly, the evaluation of the dynamical systems with mathematical background and possible applications in IoT and cryptography will be very well discussed in the upcoming 5 days. And we are going to be very useful and benefited from the expertness of Professor Lamberto Rondani and Dr. Noor Aisa Fatah. This course educates the participants to learn chaos-based data security mechanisms and highlights the applications of chaos theory in Internet of Things and cryptography. Course participants will learn this course through lectures and hands-on experiments. Also, for this we use MATLAB software, we use our lab. Also, the case studies and assignments will be shared to simulate research motivation among the participants. So I'm very glad that all the participants, those who are here from various streams, like from different IITs, NITs, central universities, state universities, and various high NIRF ranking universities of India. So it gives me very immense pleasure and to welcome you all to this program. And I wish you all the participants enjoy all the sessions during these 5 days fruitful sessions. And I thank you very much.
Thank you so much, sir. Now, I would like to invite Dr. N.K. Srivastava, Local Course Coordinator and Associate Professor in the Department of Chemical Engineering, to briefly summarize the GIAN course and its importance. Sir.
Good morning, everyone. I am Dr. N.K. Srivastava, Local Coordinator GIAN, and I welcome you all in the campus of NIT Jalandhar on behalf of GIAN program. I welcome Professor B.K. Kanojia, our director, the foreign experts, Dr. Lamberto Rondini and Dr. Noor Fateh. This is a unique course in the sense that we have 2 foreign experts. Normally, the GIAN program allows only 1 foreign expert, but with the efforts of Dr. Sivaraj, you have the means you can get the guidance and the expertise of 2 foreign experts during this GIAN program. I welcome you all once again. Due to adverse weather conditions, I hope your stay here would be comfortable. As a mandatory requirement of the GIAN program, you will have to submit the feedback for the course itself. But I would also like to request you to submit any special feedback which you would like to give during this GIAN program, as well as your stay during the campus here, so that we can make it better if you find some shortcomings in the conduct of the course, during the conduct of the course, or during your stay in the campus itself. So IIT Hyderabad is doing very well in organizing different GIAN programs. We are fortunate that we have been sanctioned 9 GIAN courses during this academic year. This is the 4th one, which has started today itself, and the program in the Department of Physics that has also started today. So in total, we have 9 courses. You can see these GIAN courses live webcast on the website of GIAN IIT Hyderabad, the website. But those who would like to get the certificate, they need to register and participate. So anybody can see the lectures live on the website of GIAN IIT Hyderabad. So this is a good initiative taken by Ministry of Education, so that you can interact and get the guidance from the foreign experts. So I once again welcome you all on this GIAN program and seek your feedback. Thank you very much.
Thank you, sir, for your motivating words. Now, I would like to invite Dr. Raghav Raman, head of our department, to address the gathering and share a few words about the department.
Good morning to all of you. Today's chief guest, our Honorable Director, Dr. Vinod Kumar Kanojia ji, guest of honor, Professor Lamberto Rondini, our special guest, Dr. Noor Aisha Fatab, local coordinator, Dr. N.K. Srivastava, course coordinator, Dr. Shivraj R, my dear faculty members, scholars, students, and participants. On behalf of Department of Mathematics and Computing and on my own behalf, of course, Dr. B.R. Ambedkar, NIT Jalandhar, I welcome you all to the GIAN course on the Dynamical System and Chaos Theory, IoT and Cryptography applications organized during the January 6 to 11, 2025. A dynamical system and chaos theory is rapidly evolving field, and it serves to the several engineering and scientific domains. Dynamical system and chaos theory is very useful to predict the future behavior of system and to control or predict the extreme, uncertain, or random behavior in bodies or events. I hope that the participants will learn a lot in cutting-edge area of dynamical system and chaos theory with real-world applications by interacting with the knowledgeable galaxy of experts during the course. As far as the department concerned, the Department of Mathematics and Computing in IIT Jalandhar is one of the 18th department of the institute. The department offers BTech and MTech in Mathematics and Computing, MSc and PhD program in Mathematics. The department teaches mathematics to BTech, MTech and PhD students belonging to the various engineering streams. The department has 17 faculty members who are actively involved in research activities in addition to the regular teaching activities. The faculty members of the department are specialized in the frontier areas of mathematics such as algebra, matrix analysis, numerical analysis, partial differential equation, mechanics, statistics, optimizations, soft computing, etc. The department till date has produced 11 PhD in different areas of mathematics, and presently 32 scholars are pursuing their PhD. Several research projects of the departments are financially supported by some of the leading funding agencies such as DST and NBHM. The department keeps in pace with the advances in technology by providing the student state-of-the-art computer facilities. The students get opportunity to attending seminar and invited lectures delivered by the eminent mathematicians and academicians. They get the opportunity for campus placement in various national and multinational companies. I am grateful to our worthy director for his constant support and motivation to make this event possible. I extend my heartiest thanks to other dignitaries, faculty members, staff members, and students of the Department of Mathematics and Computing of IIT Jalandhar for joining this event. Last but not least, I extend my sincere thanks to the participants of this GIAN course for their active participation. I wish the GIAN course a great success. Thank you. Thank you very much.
Thank you so much, sir, for sharing insight about the department. Now, with so many attributes to GIAN, now I would like to request guest of honor, Professor Dr. Lombardo Rondoni, to kindly share a few words. Dr. Lombardo Rondoni is a professor of mathematical physics at Politecnico di Torino, Italy. His research interests include dynamical systems, response theory, non-equilibrium statistical physics, astrophysics, and geophysics. He has contributed to the on-second reciprocal relations that describe cross effects in driven system. Hold even in the case of particle interacting by central forces subjected to a magnetic field. Such a discovery has various implications on the possibility of extracting work and heat from technological devices, biological systems containing magnetic particles. He has about 160 publications, including invited reviews in professional journals, 5 activities edited books, 3 books, supervised more than 30 PhDs and master's students, now employed in academia, industry, and schools, and hired 12 research associates. Sir, please.
Thank you very much for these kind words that I do not deserve, but I'm very pleased. And I wanted to show you a picture if it is possible, but if not possible. It is possible, okay. In any case, it's not important. Just put it in presentation mode.
Yes, it is ready.
Okay. So you already see it. It is a picture dear to me because it has 2 Italian famous scientists and philosophers and 2 famous scientists from India. And so, first of all, I want to thank the organizers of this important event and for giving me the opportunity to visit this prestigious institution. I really I really appreciate that. And there is that's good enough, maybe. There is a button on the bottom that puts it in presentation mode, but it's not important. So let me thank the organizers. Let me thank the local authorities for making this possible. The government of India, who is running this very smart program that is GIAN, that allows people from different parts of the world to come and share their views, and in return to get to learn about this ancient, deep culture that is the Indian culture. Okay? It is here everything begins, especially for us in the West. Okay? Everything begins here: language, religion, culture, and mathematics in particular. Okay? That's why I have Ramanujan on the picture there. Okay? Very, very important for the whole world. Mathematics is a subject, as has already been told, that is for everybody, because it is a language, or it is like art, like music. It knows no borders. Okay? There are no borders. Just personally, I apply it, as it has been said, from nanotechnologies to cosmology, to these days I'm working on muscular dystrophy and on the functioning of the nerves inside the ear, how they transmit the signal from mechanical to the brain to electrical to the brain. Okay? And of course, I cannot be expert of these things. I just know the language, the mathematics. And medical doctors come to me, engineers come to me, cosmologists come to me, okay, because they want models for the mathematical models for what they do. These days, artificial intelligence is a large field of application, okay, and some of the things that will come out in this course have applications in artificial intelligence. So. Let me conclude with a thought from Giovanni Pico della Mirandola. Let me see where he was. So, yeah, it is the one on the bottom left. Okay? Galileo, on the top right, used to say that the book of nature is written in mathematical language. Okay? And Pico della Mirandola, 100 years earlier than Galileo Galilei, used to say, we have been created for the higher things. We can choose the lower things because we are free. Well, mathematics, I think, is something that belongs to the higher things and that we can all enjoy. Thank you very much.
Thank you so much, sir, for your words. It is our earliest request to our Honorable Director, Professor B.K. Kanodia, to kindly address the participants and share your wisdom with us. Professor B.K. Kanodia currently serves as a director at NIT Jalandhar and also holds the position of professor on leave in the School of Computational and Integrative Sciences at Jawaharlal Nehru University, New Delhi, India. His academic journey is truly inspiring. Having completed his PhD in electronic engineering from the prestigious Indian Institute of Technology, Varanasi, India, Professor Kanodia's expertise and contributed to the field of academia are vast and exceptional. Before joining JNU, he served as a professor in the Department of Electronics and Communication Engineering at the Ambedkar Institute of Advanced Communication Technology and Research, Government of NCT, Delhi. Throughout his career, Professor Kanodia has demonstrated exemplary leadership in both academia and administrative roles. He has successfully supervised more than 30 PhD theses and boasts an Impressive record of over 300 research publications in renowned international journals and conferences, including distinguished publications like IEEE Transactions on antimeans and propagation, IEEE Transaction on transcendental and measurements, and many others. Notably, Professor Kanogia has been instrumental in advancing research and development projects with 4 ongoing and 7 completed R&D projects funded by various esteemed agencies of the Government of India. Additionally, he has also earned recognition for his innovative idea as the evidenced by 4 patent publications under his name. His remarkable achievement and dedication to the academic domain serve as an inspiration to all of us present here. Your insight will undoubtedly enrich our understanding and motivate us further on our academic journey. Thank you, sir.
So, good morning to everyone. So, you have seen that so many speakers is there. Na? So, why the GIAN course is conducted or organized by the Indian government? Do you think or not? So, I do not think that in everywhere everyone is aware, because we have seen the title of this GIAN course, na? The Dynamical System and Chaos Theory, na? And application to IoT and cryptography application, because I have asked our organizing team that how many participants from a computer science. So, nobody is from a computer science. Professor Sangal is there. Na? Professor Sangal is there, but I think that we are missing. Our student is missing actually the learning process. Na? That is my observation. You have seen that in a difference. Na? So, just I start from Professor Lamberto Rodino. He has discussed regarding of that a scientist, what their contribution is there. And whatever we are discussing, just we appreciate to each other. Na? So, there is a difference to how we introduce ourselves. Na? So, there is a difference. You have seen that our expert from Italy, what he has discussed at the time of inaugural and what we are discussing at the time of inaugural. Just you should think. That is my observation personally. Do not take in otherwise. And another things we have seen that in Professor Sangal is there, head of department. In how much age do you read? Sorry, do not take otherwise, because you are a younger. Huh? I think that he is 62 or 63. He is sitting here. And around of our research scholar in computer science and IT is around of more than 50. Sangal Saab, am I? 100. Na? Or I think that 2 or 3 research scholars is sitting here. They are not curious to learn. Na? That is the problem. Na? But why this GIAN course is introduced, you should think that not only you will come from 13 different states, and that Dr. Sivaraj has invite for this GIAN course. Na? So, 13, you have participated from 13 states. So many different geographical states. Na? You have come here. I have seen that you are a very young, some of research scholar or faculty member is older, but they are keen to learn. Na? You will see the difference. Na? So, whatever is going on in Italy, you have seen that in 2 scientists from Italy and 2 scientists from India, you have seen that what is contribution is there. Na? So, really you should learn that what exactly in a GIAN course, so what academic is going on in outside of India, what academic is going on in India. So, fill up of that gap. Na? So, I think that that is GIAN course is introduced in our India by the Ministry of Education. So, I think that we should learn as a researcher, we should learn in an early stage whatever they have contributing in a same area and what they contribute in their country exactly in a technical sense. No? So, then you can learn and you can go up to that level. I think that that is our main purpose to introduce of that GIAN course. I think that in a suppose in a case of a we will sponsored of a 1 or 2 researcher, they will go there and they will see that a different thing, but in a different way, if you go there in a different country, you will invite of a their expert, then you can learn. That is the beauty of that a GIAN course. I think that you will think that in a participation and a different domain. So, because this exactly the mathematics department is organizing of this time is a 2 GIAN course is there. So, I think that we should comment that in a mathematics and computing department is doing a very well in our institute. Dr. Srivastav has discussed that only 9 GIAN course in a allotted in a NIT Jalandhar, and 2 of them from mathematics and computing. I think you should give a big hand to that department. So, just this is our personal observation. So, I think that we should learn and we should inculcate of this type of a culture, and even that I am not aware that because the Dr. R.R. Sinha has discussed that in a 32 research scholar is there, and our participant is around 43. 43 participant is there. If you 43 plus 32 as discussed by Professor Sinha. So, I think that a number of student is not there. So, some of a missing. Na? So, total research student is not there. That is my observation. So, it gives me immense pleasure to welcome you all in a inaugural of the GIAN program, Dynamical System and Chaos Theory, IoT and Cryptography application. The GIAN initiative by the Government of India aimed to bring a global academic expertise to Indian institutions, helping students, researchers and benefit from a knowledge of international experts. This program, one of a 9 GIAN courses sanctioned to our institute. Dr. Srivastav has already discussed that. And a wonderful example of this vision, it focuses on an important and interdisciplinary topic that bridges theoretical mathematics with a practical application and with help to a better understanding and secure dynamic process in an area like communication, data protection and real-time monitoring. So, really this exactly is the mathematics is a Professor Lombardo Rodoni has already discussed that this is a beautiful topic in a mathematics. In a mathematics is one of a tool in any engineering branch, even that in a IT, computer, electrical engineering, mechanical engineering, civil engineering, every branch they cannot run without the mathematics. This is a fundamental tool of mathematics, and this application I think that India is very well recognized in a mathematics is strong our researcher. I think that both of our experts they will see in a across the world that Indian researcher is they are doing a very well in a mathematics. So, I think that we should encourage our student and different type of application, so they can learn. Even that we are not reach up to our research scholar, those who are interested in AI and IoT, because this application is used for a particular some of application. Because you have seen that in currently AI and machine learning that is used for a different type of application, even that in every branch they are using. But in this is a whatever they are discussing in a GIAN course, that is practically application of IoT and AI. I think that is more useful for a interdisciplinary nature. So, not on a mathematics, only the other department also like to join here. I would like to express my sincere gratitude to our esteemed foreign expert, Professor Lombardo Rendoni from a Polytechnic, Torino, Italy, and Dr. Noor Fatab, Fatab, am I right? No? Noor Fatab from a National Defense University of Malaysia, Kuala Lumpur, who is traveling such long distance to share their valuable knowledge with us. We are truly honored to have you with us. I also, thanks to Dr. R.R. Sinha, Head of Department, and Dr. N.K. Srivastav, Local GIAN Coordinator, and Dr. Sivraj from a Department of Mathematics and Computing for his effort to organize this program. His dedication and hard work have made this event possible, and I congratulate to his initiative in this regard. Even that you have seen that in one of an international conference he has organized, and lot of participants comes from abroad. No? So he is doing very well in a mathematics and computer department. I thanks to all participants. So I think that our young researchers, they should learn, they should interact with the expert, and how you will connect with them, that is also we should learn from our external expert. No? And you can work alongs with them, or even that you can reach open in a different area with their university. So suppose he is not working in the same area, those who are working, and I think that with the help of two of our expert, you can reach their colleague, then you can work in the same university. So I thanks to all participants who come from distance places in this challenging weather to attend this program. I am sure that you will be gain valuable knowledge from a session conducted by our renowned expert, and this learning with benefited your sites, study, research and future careers. Let me also take this moment, because some of our faculty and researchers comes across the India. So just I want to share some of the information about of our institute. NIT Jalandhar is spread over a 154 acre, and is home to more than 6,000 students. Our institute is known for its academic research and excellence, and holding commendable position in a national and international ranking. This year our faculty is published more than 1,155 research paper in a reputed journal, and contribute to the institute H index is 107, which reflect the quality and impact of our research contribution. Our faculty members are engaged in ongoing research project worth of more than 45 crores, have a completed consultancy project worth of 4 crore in the past year. This institute has also awarded 3 FIST project total of 5.5 crore, and established 2 center of excellence in 5G and beyond and cyber security. With a strong placement record of 90% and a highest package reached to 52 lakhs in NIT Jalandhar continue to focus on academic excellence and career developments. To nurture creativity, innovative and entrepreneurial skill, the institute has established a technology business incubation TBI and Space Technology Incubation Center STIC, funded by ISRO. Recently, the institute signed a MOU with the IIM Visakhapatnam for a dual degree program, enabling students to pursue an MBA degree online from IIM Visakhapatnam while completing their degree from a NIT Jalandhar. No problem. As a part of infrastructure development, the grant of rupees 250 crore has been sanctioned under a HEPA for a construction of 2 state-of-the-art academic blocks, hostel and residential facility. Once again, thanks our foreign expert, our course coordinator and local coordinator and department for all participants for making this program a success. I think you will enjoy, and our local coordinator, they will help you. So I wish you all the great learning experience and fruitful program. Thank you. Best wishes. Jai Hind. Sorry. Sorry.
Thank you, sir. Sir, Honorable Director, sir, we really thank you very much. Instead of your very busy schedule, you came by taking time, and you blessed us with your eminent presence. So I would like to call our HOD to present a memento to our Director, sir. Okay, sir. So I request our Honorable Director, sir, to present a memento and gift to our foreign expert, Professor Lamberto Rondani, I request Dr. Aisa Fatap also to join. Dr. Aisa Fatap, please join. One by one, one by one, one by one. First, I request our Honorable Director, sir, to present a memento to our respected Chief Guest of Honor, Professor Lamberto Rondani. I request our Honorable Director, sir, to present the memento to Professor Lamberto Rondani, the gift. Thank you, sir. Now I request our Honorable Director, sir, to present a memento to Dr. Noor Aisa Fatap from National Defense University, Malaysia. May I request our Director, sir, to present the gift to Dr. Noor Aisa Fatap. I request our head of the department, Mathematics and Computing, to present a gift to our worthy director, sir. I request our head of the Department of Mathematics to present a gift to Dr. N.K. Srinivastava, the local GIAN course coordinator.
Thank you, sir. Let's bridge the gap with education. Sorry. Let's bridge the gap with communication. Come create another aura with education. There is an end of everything, but we believe that there is never an end, but always a beginning. Thus, to conclude for today, I request Dr. Geeta Pratap, an Associate Professor in the Department of Mathematics and Computing, to propose the vote of thanks. Ma'am.
Yeah, respected dignitaries, professors, scholars and participants, good morning to one and all present here. On behalf of the Department of Mathematics and Computing, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, I am here to express our heartfelt gratitude to the people who have contributed to organize this GIAN course on dynamical system and chaos theory, IoT and cryptography application. My word may not be capable of communicating our sense of gratitude to our worthy director, Professor B.K. Kanujia, for guiding us to reach better heights and keep on motivating us in all our events as well as directing optimally towards the successful completion of the events. I like to mention here the constant encouragement of our director, sir, has motivated us to conduct such kind of technical events. We remain very much obliged to thank you, sir. So, it is great privilege for me to express our sincere gratitude to our registrar, deans, HODs and other officials who have helped in materializing the event and supported in all the approval process of various activities pertaining to this GIAN course. I would like to express my gratitude to our head of department, Dr. Raghav Raman Sinha, for his support and valuable suggestion to organize this program. Thank you very much, sir, for your valuable support at every stage. I express my deepest gratitude to the local course coordinator, Dr. N.K. Srivastava, for his support. Thank you for all your guidance to organize this course. We are deeply grateful to the chief guest of today's event, Professor B.K. Kanojia, for accepted our invitation and gracing this event with your presence. We are delighted to extend a hearty thanks to our guest of honor, Professor Lamberto Rondoni, and special guest Dr. Noor Ayaz Abdul Fattah. I am thankful to the course coordinator of the program, Dr. R. Sivaraj, for his tireless effort, dedicated involvement, tremendous planning and perfect implementation to make this GIAN course a reality. Please join me in expressing our appreciation and wholehearted thanks to all the speakers who have accepted our invitation and spent their time to share their knowledge on the most recent innovation trends and concern, as well as practical challenges encountered and solution adopted in field of dynamical system and chaos theory. We are very impressed and touched by the ability of the participant, and they deserve a round of applause. Thank you all, and thank you once again everyone. Thank you.
Thank you, ma'am. I extend my grateful thanks to everyone for making this event possible. Thank you all for joining. Now we will have the tea break. Then we will move towards our first technical session. Thank you all.
Come for the group photo. I request all the participants yes sir, we can sit sir, yes sir. I request all the participants to come forward to take the group photo with our worthy director sir and all the dignitaries and the experts.
Now, yes. Okay, this is especially for those who are online, right? Because those who are present probably can hear me without any difficulty. Yeah, please. You, no?
On behalf of the organizing committee of this wonderful GIAN course, I really thank you, Professor Lamberto Rondoni, for accepting our invitation and blessing us with his eminent presence. And he is one of the person. He is very busy, and his visit to India is not first time. And he visited many foreign countries, as introduced by Ms. Shika in the introduction. He has a vast knowledge about 3 decades, more than 3 decades, maybe I can say 4 decades. He served for education, and I personally know him for more than a decade. We had a lot of interactions. I really take this opportunity to learn from you regarding the dynamical systems. As you all know, these dynamical systems consist of many parts, not just only dynamical system. It needs differential equations, numerical methods. Not only the applied side, it also needs its fundamentals from the pure mathematics of various branches. So he has a vast knowledge, and in most of the foreign universities, mathematics department as well as physics departments equally keep this dynamical system course in their curriculum. And Professor Lamberto Rondoni is also equally associated with mathematics as well as physics departments in his institutes. So in most of the foreign universities, this dynamical system course is offered by mathematics as well as by physics departments. And Professor Lamberto Rondoni, since he is being associated with both the departments equally, not just associated, affiliated with both the departments equally, it gives us 2 things. Most of us know mathematics from the abstract side, even the differential equation, numerical methods, and many other things. We know very well in terms of academic point of view. But now we will have the chance to relate that academic point of view with prefix and suffix, because no mathematical problem is had without prefix and suffix. No mathematics exists. That's why mathematics is being developed by all the other domain people, depends on their need. The prefix and suffix is their own problem, and suffix is their own solution. We are always concerned about the body, that is the mathematics. So now we will have the chance with both the experts that we are going to have start this mathematics base with some prefix and suffix. So I request all the participants to make use of this wonderful opportunity and have a better learning in the upcoming days. So Professor, with wholehearted welcome on behalf of all our NAT family and all the participants from India, we are really fortunate to have you as one of our speakers, and session is yours, and all the 5 days is yours. Thank you.
Thank you very much. I am the one who is fortunate to be here. Okay? So I really appreciate your words, and I want to reciprocate. I'm very happy. I'm really very happy to visit this country and this part of the country, and the wonderful people that I have already had a chance to meet, and during this week maybe we'll meet more. Sure. Now, before I start, I want to give you a very quick introduction to my part of the course, because then there is the part by Professor Fatah. Professor Sivarajee will share with you these 2 folders. Okay, I don't know if you can see them. I make them larger. Okay, the folder lectures and the folder MATLAB codes. Okay, the MATLAB codes are for the tutorials, and lectures are for the theory. Now, correctly, Professor Sivarajee said that I'm involved in a lot of applications that go from academia to industry, to the health institutions, okay, and so on. So that is true, but here I will give you the theoretical background. And then if you want to know about applications, well, you know, time is short, but apart from lectures, you can talk to me personally, okay? I will tell you a little more. Now, inside the lectures folder, there is this file, which I will open in a minute, with the first lecture. And then there are various other files. Okay? They are not, they are more than you need, more than I can cover in the course. But I still wanted you to have this much, so you can go beyond what I have the time to tell while I'm lecturing. And some of these files are my handwritten notes, okay? So I apologize. I hope they are clear enough. Anyways, if anyone is interested in putting some parts of the handwritten notes into an electronic form and then share with me, that's okay. That will be much appreciated. But you don't have to do it. Okay, you don't have to do it. I'm just saying that some of these files are handwritten, and also they go beyond, okay, the scope of this. For instance, something like this. Okay, but okay, just to let you know. A number of other things are already in print. And there are a few papers. There are a few papers where the theory is explained, and there is also some application. For instance, very important applications these days are to climate. Okay? So response theory, which is what we are going to tell, using natural variability to predict forced response. In which field? In climate. Okay? What is happening to the Earth, which is one of the subjects in which I've been working for the past few years. Okay? And there are various other things. Okay? In the other folder, we will see it in the afternoon. Okay? In the afternoon, there will be a lecture there will be a 2 hours tutorial which has to do with the things. So let me start. Okay, this is 1 hour, right? So I set up the clock. No, not this one. View presentation. Okay, so here you see also my affiliations, which I have to acknowledge. Okay, so you see that I'm in the mathematics department of Polytechnic of Turin. I am in the physics department of University of Turin. I'm in the Italian National Institute for Nuclear Physics, and in Scienza Nuova, which is a new institution dealing with humanities and sciences together on the digital transition and artificial intelligence, which are very topical, as you know. Okay? And so this gives you also an idea of applications. Now, I will go fairly quickly through this file, again, because there is more than can be done in 1 hour, but I will highlight the main points, considering that also Professor Fataf will go into some of this of the subjects that I'm touching. Okay, so don't worry. However, if you have questions, you stop me at any time. Okay, don't be afraid. The purpose is not that I go through all the slides. In the afternoon, I will write at the board, okay, which is better for mathematics. But okay, this is to give you an idea that there are certain things, and each one of them would take a lot of time to investigate and to study. But it's better to know that certain things exist for those who don't already know, which maybe many of you will already know a lot of the things that I'm going to tell. So I just summarize some of the things that are important and that one could go deeper point by point. Then in the afternoon, I will start to a more systematic kind of class with calculations at the board and so on. Okay? And so we make a pact. I try to do my best, but I know that I'm limited. So, if you like, the pact consists in you stop me when I'm not behaving properly. Okay? You tell me that you have difficulties and that you would like things to be explained better. Okay? Okay. So, first, the minimum of motivation. Okay? There are a lot of phenomena that we know how to treat, that we can predict very efficiently, and a lot of other phenomena that we don't know how to treat. For instance, astronomical phenomena have become quite easy, in quotes, for us to deal with. Just think of this. I don't know if you heard, but we have placed, we meaning humanity, a camera on a comet. Can you imagine that? Can you imagine that? A small spaceship was shot out out of the Earth. It bounced back various planets. It traveled for 11 years, just using our knowledge of gravity. It traveled by itself, okay, to meet a comet that was coming from the other side of the solar system on a given day at a given time. It reached that point, and then it dropped a camera on the comet, which was traveling at unimaginable speed. Okay? And this camera sent back pictures to the Earth. So now we know how a comet looks from inside. This means that we can predict very, very accurately, okay, tens of billions of kilometers traveled by the ship, by this camera. Rosetta is the name of the device, and Philly, the camera that was dropped down. Italian mathematicians even predicted that the camera hits the comet, and because gravity is too low, bounces and finishes into a region from which it is difficult to receive the light from the sun, and so batteries would expire. It all happened. It all happened. Okay? So, for certain things, we are pretty good. Well, these are far away phenomena, right? While we cannot predict in the same time phenomena that are close to us, like the climate, which is one of the subjects in which I work, one of the applications. Okay? And for that, I work a lot with environmental engineers, for instance. So there are various kind of situations that we can meet. Some are those in which there are laws that are known to us. Newton's law of gravitation is what I just mentioned. Okay? There are situations in which laws probably exist, but they are not known to us. For instance, earthquakes. We know that the crust of the Earth has got a certain structure. We know quite a bit about that, and nevertheless, we are not able to predict an earthquake. Okay? Then there are situations in which probably laws don't even exist. And the financial market probably is one of those things. There are various opinions on this. Okay? Some people will say that, yes, there are the laws, but they are complicated. Other people will say, if there are the laws, then people would find a way of going against them, so in the end, they are not laws, and so on. Okay? I don't know. Now, in the mathematical description of these things, we have two main ways of proceeding. One is deterministic. You give me the initial condition, I tell you what happens after some time. Okay? And the other one is probabilistic. I cannot tell you where you will be after some time. I can give you the probability of you being somewhere after some time. Okay? in these classes, I will combine the two. Now, just to mention another application which is very popular, I should speak of artificial intelligence. I just give you the title, okay? But you can see the search for a pattern, for reconstructing a picture, or for finding out about, how to run an airport at a certain time of a certain day, where just the human brain is not fast enough to take the decisions that are. You can stick it in, yes, yes. Ah, for this thing, okay. Continue, is not identifying. So I just continue while it sets up. Yeah, but now, yeah, okay, let me see. Yes, perfect, thank you. So you can see it as a dynamical process. Okay, here I have a slide on a model of guessing an unknown function f, starting from knowledge of it on a few points. Okay, and this function f could be whatever you like. Could be the picture of a cat, okay, or could be the sequence of airplanes that have to land. Okay, whatever you like. Well, you can cook up a dynamical model, a dynamical system in which the parameters that you will use to define the function have to converge through a certain rule that now I'm not going to explain, to a final object. The final object is our guess of the cat or of something else. Okay, so dynamics comes out even in here, and some of the things that I'm going to tell you, I'm not an expert of artificial intelligence, but I tell you there are experts of artificial intelligence who are using the tools that I have developed together with other colleagues, for instance, from Australia. Now, there are dynamics that are simple, but a lot of dynamics are very complex. In particular, they could be chaotic, which is one of the key words. Okay? They can be chaotic. They are characterized by what is called the butterfly effect, that trajectories diverge from each other exponentially fast. Okay? It means that if, for instance, I want to throw an arrow or a dart to a target, and I aim very, very precisely, okay, that it seems to point directly like this, well, in fact, I will have a little uncertainty in my aim. And this uncertainty will, at some point, explode so that I don't even know if I hit the target. Okay? This is something like chaos. But we'll say more about that. So to deal with this kind of situations, okay, there are various indicators, for instance, Lyapunov exponents. Okay, this poses some limits into doing what we would like to do with machine learning, or some time ago we called big data. Okay, learning from past, because you lose memory of the past. Sometimes having many parameters, rather than make it more difficult, it helps. Okay, but this is just to say. Okay, so this is for the introduction. Now, what do we say about dynamics? There are two kinds of dynamics that usually we look at. Okay, there are continuous dynamics. They are called flows. Okay, a flow is the solution of a differential equation. I will always have ordinary differential equations that are autonomous, no explicit dependence on time. That can be treated, but it becomes more difficult. Okay? So I have something like this, where my variable x, which could represent what? The temperature of the Earth in Jalandhar. The temperature in Jalandhar. Okay? It will follow a certain equation. In fact, they make predictions about what it will be tomorrow. Okay, or it could be the position of the camera on the comet, or many other things. Okay, for notation, the solution, the flow, given a certain initial condition, time t can be denoted like this: the initial condition and an operator phi t that evolves. And this phi t obeys properties of semi-group at least. Often it is a group. The phi t composed with phi s is phi t plus s. If you advance for a time t and then for a time s, is equal to advancing for the time t plus s. You may think that it's obvious, but not always. This is continuous evolution. Okay? Then you can, however, transform the continuous evolution into a discrete one by taking a section in space. You know that the trajectory comes like this. You put a surface, and you look when it hits the surface, and you get one point. Then the trajectory goes around, 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 and hits in another point later on. Now, if you follow the points that are being hit by the trajectory, you will have a discrete dynamics, and you will have a different kind of mapping that at different times gives you the different positions. Okay? But discrete dynamics can be justified by itself. For instance, you find a lot of interesting websites about the logistic map. And here I listed a few of them. Okay? So you will have, when Professor Sivaraji will give you access to the folders, you have these kind of things. Okay? What is the logistic map? The logistic map is the simplest or the best known discrete dynamical system that jumps from point to point. Okay? It jumps according to a very simple rule. You have your point xn, and you want to know what it will be after one time step. It is defined in the interval 0, 1, so it is a number. It is a number. What is this number? It can be many things. Okay? For instance, if you rescale it with this, you can get to count the generations of rabbits that you can have in a factory. Okay? Put between 0 and 1, but then you expand, okay? And you get something like that, because they have an evolution that can be mimicked there. Or it could be the time intervals at which light is absorbed by our eyes. Okay? So it is something trivial, but not that much. Not that much. It is mathematically trivial. What is trivial? It is just a parabola, you see. Mu is a constant between 0 and 4. And x is a number between 0 and 1. So you draw between 0 and 1 a parabola. You take xn here, find the parabola, and you have xn plus 1. That is how it goes. This picture is for mu equal 3 and for 2 initial conditions. It is important to look at the rate of variations, which are the derivatives of this, and you will see what happens. Now, we call, for the dynamics, what is the simplest of trajectories? The simplest of trajectories is the one that does not move. It is called a fixed point. Okay? So if x bar is a fixed point for a flow, it means that the function f, the vector field, is equal to 0, so that the evolution at any time t remains what it was. The next kind of object are the periodic orbits. Okay? The periodic orbits, they are not fixed. They are fixed after a certain time t, which is the period. So if you evolve for a certain time t, you go back to where you started. Fixed points and periodic orbits form what is called a set of critical elements, here indicated by gamma phi. Okay? And then there are points that are not fixed at all, and they are not even on a periodic orbit. They are called wandering points. Okay? What are the wandering points? Well, a point is wandering if it has a neighborhood ux such that, this is the definition, ux is the neighborhood of my point x. You start inside ux, and now you intersect the trajectory with the evolutions of this set u for all times larger than a certain time t0. Now, if the intersection between where you started and where you are going is empty, then it means you are wandering. You don't come back. Okay? These points form an open invariant set. What is an invariant set? An invariant set is a set that does not change under the application of the dynamics. Okay? And then there is another invariant set, which is the points that are not wandering, the other ones. Okay? If you belong to the wandering points, you stay in the wandering set. If you belong to the non-wandering set, then you will be points that violate this condition. There will be some time at which you come back. Okay? Now, among the invariant sets, you have also these ones. You have attracting sets. What are attracting sets? They are sets that, that you have if there exists a neighborhood U such that for every other set containing the one in question, okay, the evolution of U will end up inside V. So because this is for any V that contains A, it means you can squeeze as close as you like towards A. And in that sense, A then is attracting, because you start from outside and you end up as close as you like. Because it is an invariant set, for what I told you before, it means that if you start inside, you remain inside. If you start outside, you remain outside. You don't go inside the attracting set, but you get as close as you like. Okay? And then in that sense, it is called attracting. Then this set is called the fundamental neighborhood of A. Okay? Is the one that has to exist. The union of the evolutions of all these sets is called the basing of attraction. It is all the points that will end up as close as you like to A. Okay? An invariant set which is not attracting is called repelling. It doesn't want you to get close. Okay? And there is a very important property which is topological transitivity, which links with what is called ergodicity. I will tell you a little bit about ergodicity in the coming classes. Okay? If there is a dense orbit in this set I, then the evolution is called topologically transitive. Dense means that you can go everywhere. That's why it is transitive. And that implies a property known as ergodicity, which we'll mention further down. Now, an important, very important theorem connected to these definitions is the Poincaré recurrence theorem. Okay? Suppose you have dynamics that preserves the volumes. What does it mean? It means that you take one set, you have to have a metric space, you have to be able to define volumes. Okay, you take one set, you evolve all the points of this set, the evolution will change the shape, but the volume will remain the same. Okay? The theorem is more general, but this is how Poincaré proved it in the early 1900s. Okay, so if you have a volume-preserving set, for flows, it means that the divergence of the vector field is 0. If any of you are familiar with hydrodynamics, then they will recognize that this is a condition of incompressibility of flows. Okay? And you can do it also in an abstract space, totally abstract. Okay? Say we are speaking about the temperature, or say we are speaking about the times of reaction of the eye to light. Okay? It's not a fluid, but you have equations that describe that. Okay, so if you have volume preserving, and D is an invariant bounded set, okay, then for almost every x in D, almost every is a notion of real analysis. You may be familiar, but we speak of the volume, and so it is for the volume measure or the Lebesgue measure equal to 1, meaning you exclude a null set. For almost every x, you have that the lim-inf for time that goes to infinity of the evolution of x minus x goes 0. So points come close, okay, as time evolves. It means that you started at x, then you go around, round, round, but at some point you have to get back close. Note, it's not the limit, because it does not mean that you approach that point. But it means that in time, every now and then, you get even closer than you had before. So it is the lim-inf. Goes to 0. If you wait enough, you will get as close as you like. And then you wander around, but then you come back. Okay. And then there are other kinds of sets. I don't, okay, there is a whole list of sets. So, most important ones, or simplest to treat, are attractors, anti-attractors, and repellers. Okay? And they are called so, did I say in decomposability? Yeah, well, in decomposability, it means that they are transitive, okay? What I told you before, that you can go around everywhere. So you have these three situations. If you have in decomposable set compact, when it is attracting, it is an attractor. When it is anti-attracting, if you go forward in time, you go away rather than, okay? If you go backward in time, you get close. Okay? This means anti-attracting or repelling, okay? The different basins of attractions are separated by other invariant sets that are called basins boundaries. They are at the boundary between different regions that attract, and so they are undecided, they remain there, okay, on the edge. A little bit to the left, they go left. A little bit to the right, they go right, and they are just precisely there. They are invariant sets. Now let's take a look at the logistic map, because for that it's possible to do very simple calculations. Okay? Here you see for mu equals 0.8, which is less than 1. Okay, you remember what was the definition of the logistic map? Do I have a marker? But otherwise, yeah, thank you very much. So was x n plus 1 equals mu, yeah, xn 1 minus xn, okay? This is the map. So if mu is less than 1, the derivative of our parabola at 0 is lower than 1. So this straight line of slope 1 stays above. Now, if you want to follow the evolution, what will happen? You start from one point, okay, and you get to this other point. Now you are at this point, and you go and you get to this other point. And you see you are gradually converging towards the 0. But if you take mu bigger than 1, like mu equal 2, then you see that the situation is different. Okay, you start here, you go here, and then you go towards this other point. Now look, this point and this point are fixed points. Why? Because the map is equal to the point. Because this is the line y equals x. So y is equal to x. It means the point has not moved. Has not moved. So they are fixed points. You know the fixed points of a map of the interval. You look where they intersect the line of slope 1. Okay. Now you can compute what the fixed points are. Okay. Given that equation there, x equals 0 is always a fixed point because the straight line and the parabola always meet at that point. Okay. But then when mu is sufficiently large, okay, there is another fixed point, which is 1 minus 1 over mu. That arises only for mu bigger than 1. Because if mu is less than 1, you get something negative, and negative is outside of your space. You cannot reach anything that is negative, because the parabola maps everything between 0 and 1. Okay? So you need to have mu bigger than 1. If mu is bigger than 1, you have 2 fixed points. Okay? What has happened is this. This axis is mu. Okay? This axis is mu. For mu below 1, you only have 0 as a fixed point. 0. Okay? But when you cross the value of 1, mu equals 0 remains. But then there is the new other point that you see has got this shape. Okay? What happens in addition? It happens that as long as mu is less than 1, the derivative of the function at 0 is less than 1. And that derivative being less than 1 produces the picture that I've shown you earlier. Okay? That you converge to 0. But if the derivative is larger than 1, you converge to the other point. So derivative being equal to 1 makes a difference. Okay? It's called a bifurcation. You go from 1 point to 2 points. In this case, it's called transcritical bifurcation. I'll give you very rapidly. Okay? Just on bifurcations, you will need a course of 100 hours. But it's good to see what they are. A few bifurcations. What corresponds to? Corresponds to the variation of the numbers of fixed points or of periodic orbits. You can consider a periodic orbit as a fixed point of a different dynamical system. Okay? In the case of this, call this f of xn, then the fixed point is x are the points that verify this. You apply f and you don't change. Okay? But you can do something more. Suppose that you have a point x0 that goes into a point x1 that goes into a point x0 again by applying the map f twice. Well, then what you have is that f applied 2 times does not mean raised to the second power. Okay? It means I iterate twice, f squared of x equals x. Whoa, f squared is another map. F of x equal x. So the periodic orbits of period 2 can be seen as fixed points of a different map. Okay? So speaking of fixed points is good enough to speak also of periodic orbits under many respects. Now here, as I told you, there is a parallel between discrete and continuous dynamics, so I give you some examples of continuous dynamics. The first one, and I show you also only those that are called codimension 1 bifurcations. Okay? That means there is only one parameter that produces the bifurcation. Okay? So, for instance, if you have an equation like this, u dot equal mu minus u squared, okay, you will see that for mu less than 0, there are no fixed points. Because this is a flow, you should have u dot equal 0, but if mu is negative, you cannot solve this equation equal to 0. Okay? So you start from any point and the equation pushes you down. Now you change mu, you come to mu equals 0, you can have at least one solution, u equals 0. And if you move further, you have 2 solutions. So for mu equals 0, only one fixed point. For mu bigger than 0, 2 fixed points. And you see which ones you converge to and which ones you go away from. This is a saddle node bifurcation, as it is called. This is the transcritical bifurcation, which corresponds to the passage from one fixed point of the logistic map to 2 fixed points. The pitchfork bifurcation, we will see it again. What happens here? you start from having a single fixed point, then you come to a value of the parameter at which two arise. Okay? Or you go from two to a single one. Okay? Pitchfork because of the shape of this thing. Okay? Hop bifurcation is very important. You know, a very, very, very famous neuroscientist from Rockefeller University asked me to discuss a problem about transmission of signals in the so-called tip links, which are tiny objects connecting the cilia in the ear that transform a mechanical signal into an electrical signal, where he has already found that there is a phenomenon corresponding to a Hop bifurcation. Of course, he's a neuroscientist, not a mathematician or not even a physicist, although he knows a lot of mathematics and a lot of physics. Okay, I don't want to spend too much time on these things, I told you. But you see, the situation is like this. You have a trajectories that spiral in to a fixed point. Now you change the parameter, and these trajectories don't spiral in anymore. They may start to spiraling outside. And you go from fixed point to periodic orbits that can be either approached or moved away from. So, for the logistic map, you have something of that sort. Okay? You remember that for mu bigger than 1, you have this second fixed point. Now, if you continue to change mu, you arrive to this point, where this fixed point continues to exist but becomes repelling. Like this one continues to exist but became repelling. And when this fixed point becomes repelling, two new points become attracting, and these 2 points belong to a single orbit. If you start here, you jump here, and when you are here, you jump back to that. Okay? And you see that you have drawn a pitchfork. And the points remain throughout, but they have doubled in number. Okay? Period 1 turns into period 2. And that happens for the logistic map, you can compute exactly. Okay? When do you have two solutions of the twice iterated map? Okay? You solve this little equation, and you find out that you have to be larger than 3. Because for mu smaller than 3, this is imaginary, it is complex, it is not a solution. How does this thing come? Let me show you in pictures. Because sometimes pictures help more than the mathematics, sometimes the mathematics helps more than the pictures. It depends. Put together, they work much better. So, this is F2, okay? This is F2. F1 is a parabola. F2 is a curve of degree 4, because you apply the parabola twice, okay? So it has degree 4. Now, it looks like a parabola that is a little more flat. This is 0.9, like I gave you earlier. It was a little higher. What happens if I increase mu? Well, if I increase mu, you see, the shape of the parabola starts to change. It starts to do this. Why? Because degree 4 means it must come to a point of having 4 solutions. Well, to have 4 solutions, you have to have some bumps. And mu equal 2.5, you still have only 2 intersections. The 0, which is also period 2, because you go from 0 to 0 and to 0 again. And that fixed point, 1 minus 1 over mu. Still a fixed point, you go from it to itself and to itself again. But you can see that if you do it again, see what happens? It happens that mu equal 3 the point where other orbits are coming, the map and the straight line become tangent to each other. Now here you can say that you have two coinciding solutions. Okay? And if you go further, they split. So the fixed point remains, but now you have two new points, and these two are not fixed points. They are fixed points for the twice iterated map. So these are points of a single periodic orbit. Okay? That is how it happens with the mathematics. And you see that it is crucial the step at which the derivative becomes 1. Okay? Which is what I showed you before. Now, at 1, the fixed point becomes unstable, repelling, and the orbit that is born arises as an attracting orbit of period 2. Okay? In fact, you can quantify these kind of things by looking at what iterations do. Okay? If I have a point x hat, okay, I ask if after the application of the map of a point to a point that is close to x, not exactly, you add a little h. Okay? Will the distance between the two, x plus h and x, initially the distance is only h. Okay? If I apply the map, will the distance be larger or smaller? Okay? So suppose that it is larger the initial distance, so you go to a shorter distance, you are converging somehow. Okay? I don't know why I wrote this twice. Because this is a fixed point, so it is equal, x hat is equal to f of x hat. Okay? Well, look at what you have written. Divide by h. There you get 1. You get 1 larger than the absolute value of this. Wow, but this, for small h, is the derivative with an absolute value. So 1 and minus 1 play the same role. If you want things to get closer, you have to have the derivative smaller than 1. Okay? And now you can repeat for n iterations, which will apply to orbits of period n. Okay? You can repeat. But now, the derivative of f of n, what is fn? Fn is equal to f composed with f, composed with f, n times. So it is a function of a function of a function. You apply the chain rule, and you have the rule. Now, the map is Fn. 1 has to be larger. If you want to converge to an orbit of period n, you need the derivative, which is this chain rule, smaller than 1 in absolute value. Here, sorry, I didn't put the absolute value. Okay? And that is what is not very difficult. It is the derivative in the first points times the derivative in the second point times the derivative up to the derivative in the last point. So you only have to do derivatives and follow the trajectory. Okay? And then things can become very complicated. Then you have situations with different kind of bifurcation, saddle node, in which you don't double the number of points. But for instance, you produce an orbit of period 3. And these two orbits make, and in fact, it's not a single orbit. They are two orbits that are quite close to each other, almost overlapping, but one is attracting and the other one is repelling. So you still have an even number of points, which makes 6, but is not a multiple of 2. Sorry, is not a power of 2. Okay? And this is, you may have seen this many times. Okay? It is the whole thing. When you reach 4, you have infinitely many orbits of all periods. Plus, they are a countable set, plus an uncountable set of orbits that are not periodic. And that is fully chaotic region. Okay? one-dimensional objects, of course, are very simple. Usually you have many more dimensions. The next step out of 1 is 2. And with 2, you already see a lot of things. With 2, for instance, you can define stable and unstable manifolds. They're not guaranteed to exist for all dynamical systems. It depends on the properties of the dynamical systems. Okay? But you can define a local stable manifold. S is for stable, loc for local. It is a property of the point x0, which is all the sets in our space, such that if you go forward in time, the point x0 and the other points in the set get closer to each other. Okay? This does not need to be a fixed point. Okay? It moves. X0 moves in time, but it brings with itself the other points that get closer and closer. Okay? For instance, this could be a periodic point. It goes around. It doesn't stay fixed. And then you will have other points that chase x0. Okay? Unstable manifold is when the two get close but going backward in time. So locally and for a short time, they move apart from each other. Why do you define it for going backward in time? You say they get close going backward in time rather than say they get far apart going forward in time. Because your space, I went through quickly, but typically is compact, bounded, okay? And then you cannot move apart forever because you will reach the boundary of the space. So it is misleading to think that the points get far away from each other. Also because there is recurrence. So points sooner or later will come back closer to where they were. Okay? But if you go backward in time, they can get as close as you want. So this is the unstable manifold. Local, because they're based on a point. Global, when you take the union, okay, of all the local ones. These are very important for chaos. Okay? These are very important for chaos. The clearest notion of chaos is that of hyperbolic dynamics. Now look, hyperbolic here is not the same, is not in the same sense of PDEs. Those of you who work with partial differential equations know that there are hyperbolic, parabolic, elliptic kind of PDEs. No, this is a different thing. It's related to the fact that trajectories draw kind of hyperbola. Okay, the trajectories do things like this. Okay, it is in this sense. How come? Okay, you take an invariant set, say I. It is called hyperbolic if for every point in it, the tangent space of at x in your space M can be split in 3 linear spaces, which correspond to unstable trajectories, neutral trajectories, and stable trajectories. What are they? There should exist a constant k bigger than 0, and another constant c that depends on 2 points on the space, the point of interest, x, and the other points in the set, okay, that are both positive and continuous. This one is positive and continuous. And they verify this for every x in the invariant set and for every time bigger than 0, for every vector in the stable space and for every vector in the unstable space, what does happen? It happens that the evolution, this M, is the evolution in the tangent space, okay, of the stable vectors gets smaller and smaller in size. In fact, it gets exponentially smaller, okay, than the initial size. In the unstable space, the vectors become exponentially larger, plus gamma is the angle between stable and unstable. This angle should remain bounded away from 0. So it is called hyperbolic if you have a structure like this of the dynamics. This is your x. X, yes. And these are any other x prime. Okay? If around this x the moves but brings with itself all the other points, trajectories goes like that. They approach and then they go away. This is the stable space. This is the unstable space. Okay? And it is important that these two spaces have an angle, gamma, that never goes below a certain value. Because stable and unstable manifolds should not get confused. It is also quite contradictory because on one hand you want to expand exponentially fast, in the other side you want to contract exponentially fast, so you have to avoid that. But if you have this situation, okay, then dynamics are really exceedingly complex, and you can call them chaotic. A characterization of chaoticity in whatever number of dimensions is given by the so-called Lyapunov exponents. Okay? I'll give you the Lyapunov exponents later. But basically, the precise definition. But basically, the Lyapunov exponents are the rates of expansion when they are positive, e to the lambda t, lambda bigger than 0, belongs to the unstable manifold, e to the, let me call it, well, let's say lambda I, and then lambda j, e to lambda jt, for lambda j less than 0, that corresponds to the stable directions. If you have that hyperbolic structure, what happens is this, is that the positive exponents are separated, apart from one that could be 0, apart 1, okay, they are separated by a value k from the negative exponents. That comes from the hyperbolic structure. Okay? So what you can have is a certain number of positive exponents, bound k. Okay? Larger than, forget about this, which is present in flows, not present in maps. Okay? The next step is the negative ones are smaller than minus k. So there is a positive distance between positive and negative exponents. That causes a lot of chaos. Okay? Maybe I have a picture at some point. Well, this is for the logistic map to show you that you can easily compute the Lyapunov exponents. Okay? Because you remember you have just to compute the derivatives. And it is easy to see that distances near a fixed point contract exponentially with the parameter mu, and you can write this mu to the n as lambda e to the lambda n, and that will be your lambda. Okay? Now, depending on where you are, this lambda will be negative or positive. If it is negative, you're speaking about a stable orbit. If it is positive, you are speaking of a non-stable orbit. In the logistic map, you even have a situation in which lambda goes to minus infinity, and that is called superstable. In one iteration, you go from 1 to 0 in one go. Okay? If somehow you reach 1, you put 1 here, the next point is 0, and you don't move anymore. It is super stable, because more stable than that is impossible. Let's see what happens if we change the parameter. Here it is called R. Sorry, but this R is the mu. And in red you see the trajectories, right? So for r equal 1, this fixed point is still attracting, but just marginally because parabola and straight line have become tangent here. The derivative is 1, so you are in a marginal situation. Now let's see what happens to the trajectories starting from the same point as I increase r, okay? You see, we are in the situation, let me go back a little, in which there is a single point that attracts, it is this one. It is the one that was called 1 minus 1 over mu, or the r, okay? But if I go a little further, you see this is 248. Remember that something happens at 3. What? Got stuck? It goes back. Ah, yes. Okay. You see, you have created periodic orbit. Now you go around. Okay? But these periodic orbits now at 318, maybe they're not stable anymore already. Okay? In fact, you see, these are the period 3 orbits that I showed you earlier. Okay? And if you continue, it becomes very chaotic. Okay? This I will skip. This is the slide of indecomposability. Never mind, I skip it, okay, because there is a lot. I just want to show you what happens. How come that you can, one way of producing very complex dynamics, okay, are the so-called homoclinic and heteroclinic intersections. What are they? They are intersections of stable and unstable manifolds of a single point, homoclinic, or of 2 points, heteroclinic. So what you can have is a situation like this, for instance. This perhaps is simpler. You have a fixed point which has one unstable manifold, this one. If you sit in this direction, you will move away from the point. And a stable manifold, okay? The point is fixed. So points on the green line, either they get close or they move away. But remember that the space is bounded, is compact, and so they cannot go too much away from the point. We'll come back at some stage. So along this path, you find points that move away, and when you come here, you find points that move toward. Now look, they don't follow this trajectory. Okay, they don't follow this trajectory. This is the set of points that eventually gets closer or further away. They don't follow this trajectory if you have hyperbolicity, because if I sit here, I will move transversally to that. I will do this kind of complicated shape. Let me see. Yeah, this is the fixed point. You will do, try to think of this picture, okay? You will do this kind of oscillations around the stable and the unstable manifold. Now you see what happens. It happens that if you are on the stable direction, say you are in this point, the next step takes you down here. Then you turn around and you have got closer. Then you go around and you have to get closer. Why? Because you were in the stable manifold. So you want to get closer, eventually closer. But as you get closer, you do this kind of wrinkles. Now, because of this, as you go down this direction, you start to become parallel to the unstable manifold. While you get closer through the stable manifold, you get further away through the unstable manifold. And so in one direction you get closer, in the other direction you get far away, and you can imagine that these lines here becomes dense and extremely long. And what does that mean? it means that you cannot predict what will happen. Because this is the point, the fixed point. And these are the many trajectories that I don't draw all of them. Now they accumulate close to this point. They will become infinitely many. Infinitely many. Now, when I do an observation, I do the observation with a limited accuracy. So I don't know if I am in this one or if I am in this one. Okay, so say I have a little uncertainty like this. Imagine that this can be as small as you like, because before you reach this point, you have gone back and forth infinitely many times. So you say, am I here, or am I here, or am I here? Because if I'm here, I will move in this direction. And if I'm just a tiny bit moved apart, I will move in this direction. Where do I go? I don't know. That is chaos. Okay? It is one way of producing chaos. It's not the only one. Okay? Now I have a list of possible models that you can study in the tutorial. I just show you quickly because the hour is about to finish. Just to show you, here it is explained about their bifurcations, attractors, and so on. Okay? And in the lecture of the afternoon, I'll tell you about invariant measures, which here are computed for the logistic map. Okay, so at this point, you will find the analytical expressions for the simple case of the logistic map that can be computed, everything analytically. In the afternoon, I give you the general theory. Okay, so this we can skip because you just go, and when you are in the tutorial you do these things. I just want to tell you two things very quickly, to which we can go back whenever you like. So, because of this impossibility to make a prediction, even if the dynamics is totally deterministic, right? You understand that this is totally deterministic. There is no uncertainty in this expression. But the uncertainty is in our ability to follow where these dynamics will go. The dynamics will go where it has to go, but we don't know. Okay? There is difference between the phenomenon and what we understand of the phenomenon. Okay, so because of this, our own uncertainties, we will do better to use probabilities. That I explain in the afternoon. But the term that I call ergodic, to which we return, has got to do with this. That if I do a time average of a certain quantity along a given trajectory, this bar means I average in time. What does it mean? I divide by the time and sum over all what I observe along the trajectory in time. So this is time average. The time average becomes equal to an average with respect to a given probability. When you can do that, the dynamics will be called ergodic. Okay, this is one thing. The other thing, which I'm not going to do, but in the slides you find done for the logistic map, and then the handwritten notes for the Baker map. The Baker map is a bit more complex, but also gives much more satisfaction. Okay, the idea is this, is that because, how can you quantify this loss of determinism in favor of probability? Well, for certain maps, which are isomorphic to Bernoulli schemes, for those of you who know about stochastic processes, otherwise don't worry. Bernoulli schemes are extremely stochastic systems. Okay? What you can see is something like this, is that you give me an initial condition between 0 and 1 with a number of digits. If these are expressed in binary language, okay, in binary, not in decimal language, then the evolution of the logistic map can be transformed into an operator which is very common in functional analysis, which is the shift to the left. You go from a number to a sequence of symbols where the AI are equal to 0 and 1 only. And you know what is one iteration? One iteration means erasing one symbol and shifting to the left. Very simple for very complicated dynamics. If the dynamics are not sufficiently complicated, this does not happen. Okay? The isomorphism does not happen. You want something exceedingly chaotic. But if it is exceedingly chaotic, you can transform the dynamics in shifting the digits. But now suppose you know the position of your point with 100 digits. And from the 101, you don't know what you have. After 100 steps, you don't know where you are. Okay? And with this, I stop. Thank you very much. And usually, you don't have 100 digits. Okay. Thank you very much. You didn't ask any questions, but I'm happy to answer now, although this morning we started a bit late, but I'm here for you.
So any questions from the participants? Feel free to ask. You are here to learn. If there is any questions from the participants.
Well, you look at the material. If you can make the 2 folders available, right?
Yes, yes. Thank you to everyone. Yeah. So thank you everyone. So now hereafter I hope everyone you are having the schedule with you. We go exactly as per the schedule, and small request, Professor, you can please sit.
Yeah.
And small request.
I can switch it off.
This is actually the live is going on, video recording. So it is a humble request that please don't move like this. If by chance for any reason you want to move, you go this way, and from the back side you go. And whatever the schedule is mentioned hereafter are the classes as well as the tutorials as well as the sessions will start very exactly. No more difference will be there. So 1 or 2 minutes or 5 minutes early, you please come and get settled. And for the lunch, I hope all the participants, please sit.
Yeah, but then this makes noise. I'm happy to stand. It doesn't bother me.
For the lunch, I hope you all know for all the girls, it is arranged in girls' hostel or guest house where you are given preference. And for the boys, it is arranged in the boys' hostel or guest house where you are given the preference. And for others, few of you like made own arrangements. You have 3 possibilities: either girls' hostel, your girls or boys' hostel, or the guest house, or these centers. And for any other reasons or anything, you can contact us for any time. And like I hope you all are almost there with heavy winter jackets, everything to face the weather. And it is maybe a little bit different for others, those who come from different parts of India. But those who are around Punjab and the nearby states,
They know.
it might be very easy. You are handling regularly. And all the this course kit that you would have received. There were 5 participants. They did not receive the kit. Just now, after this, if you come with us, we will be giving you the course kit. And then the tutorial will happen over there. By chance, you could have come with your laptop, own laptop, with MATLAB installed. You can use your own laptop. If you don't come with your own laptop, you can use our systems. In all the systems, MATLAB installed. So it is your choice. Whether you want to use your own laptop or the systems is your choice. So the tutorial will start at 8:30. But before that, we have one more lecture. The lecture started at 2:10. It is now actually 1:42. So only this time you please adjust. After that, everything will go as per the time. So please come. The lecture will start at 2:10. So please come by 2:10. You have about 30 minutes time.
Maybe for the first day we can delay a little the beginning, so there is time to eat something.
The tea time will reduce. So yeah, the lunch will be difficult. So 1:40, 2:30 is okay.
2:30 could be.
2:30. So 2:30 you will get 15 minutes time. So please
Yes. Perfect. So today we are running a little late, but I think it is understandable. So. Now, as I told you, so I take a few minutes to see if more people show up. For those who are present, as I told you in the morning, you find, well, actually it was already afternoon. In the two folders, you find the presentation that I showed earlier, and also quite a bit of other material. So you can look at that. I know very well that I was fast, okay? But as I mentioned, the purpose was not so much to explain all details, but to make those of you who aren't already aware of those kind of structures that you find in dynamical systems. And those of you who already know the stuff, maybe they have just seen it in a slightly different fashion. Okay, there are things that you find in many books. So someone actually asked me about the literature. So I put something in the box, in the Dropbox. Maybe this is on? No, because when I come here, yes, this is off. Yeah. I don't know. Let's see. But okay, something behind. But if it doesn't bother you, I try not to get too much on this side, yes, because seems, yeah, okay. Well, let me delimit our space. So about books, there is a whole variety of books that you can choose, whether more mathematical or whether more applied and so on. Now, I don't remember exactly the titles of the books, but I remember some of the authors, so I write here some of the authors. Okay. Strogatz is one author. He has a book on dynamical systems and chaos. Then there is a group of 3 of my friends from Rome, Cincini, Cecconi, Vulpiani. They have another book on dynamical systems and chaos. I think that the title of the book is really Chaos. These are very good books. This has very interesting applications. This is a classical book. If you want deeper mathematics, then there is a book by Ruel that is called Differentiable Dynamics and Bifurcation Theory. Something like that. Still on the mathematical side, but a little different, there is Holmes and Guckenheimer. This is also about bifurcations and dynamical systems. Yeah, I mean, there are many. Still more on the mathematical side, you have Ricardo Magnet, that is about ergodic theory. Okay? In any case, if you want to know more, you ask me. Plus, you have the material that I gave in the book. So, maybe it's time I start. Huh? Okay. and those who come in case they ask me later. Okay, so now what I want to do is to start to build this probabilistic or statistical theory of dynamical systems. Okay? And I gave you the motivation at the end of the previous class. The motivation is that when dynamics get too complicated, you cannot make predictions. You struggle, you work as hard as you like. But if you have exponential separation of trajectories, so if you have positive Lyapunov exponents, then after a short time, you have to resort to a different approach, which is statistical. It is probabilistic. It is very precise what we will do. It's not that it is sloppy. For instance, for weather forecasts, I'm not sure about Jalandhar, but for weather forecasts, you have a Lyapunov exponent. You remember the Lyapunov exponent appears in the exponential e to lambda t. So dimensionally, this is the inverse of a time, because the exponential must be taken of a pure number. So this is time, then this must be 1 over time. Okay? So for weather forecasts, more or less, you have a Lyapunov exponent of 1 over a week. So if you want to do predictions that go beyond the week, tough. Good luck. Okay? You have these weather services that they give you, even on my phone, they give you forecasts up to 10 days, sometimes up to a month. Okay, don't trust them. If they get it right, which is not impossible, it is because they rely on something else. And most, they could be relying on good luck. But, you know the pattern of weather more or less in a place, so you can try to get something like that. The forecasts of climate over the years, that is a totally different story. Okay? It goes beyond. It goes beyond the possibility of studying dynamically things. But what they do, and you find it also in your phones, is they give you the probability that something happens. Okay? And then what do you do with the probability? Whatever you like. We warn you. Okay? We tell you, look, there is a probability of 99% that it will rain tonight. Then you take an umbrella. Then if it does not rain, they didn't say anything wrong. Okay? They didn't say anything wrong. Probability, this would also take another course of 100 hours, is a very useful, extremely useful concept of something that doesn't exist. Okay? There is even a British famous probabilist who these days has written a paper or has been interviewed, I don't know. No, I think he's written a book, maybe. And the title is something like, Probability probably doesn't exist. But, subtitle, but it is a good thing to do as if it exists. So I will take you through this path. Okay? Remember that probability, I would say a little more than probably doesn't exist. I would say probability doesn't exist, which is what one of the greatest probabilists, an Italian, Guido De Finetti, has stated. It comes from the tradition of Bayes. Okay? Probability is a rational scheme, something that is in your mind, not something that you touch. In which sense it doesn't exist? It does not exist in the sense of this phone. It's not material. Okay? If you want, I have one paper I could give you to you about when probability turns material. If we are lucky, by the end of this course, I tell you something about that. Okay? It's not like a stone. Okay? If I throw you a lump of probability, it doesn't hurt you. If I throw you a stone, maybe you don't like it. Two different, very different. But nevertheless, we want to use probability as something concrete in those cases in which there is nothing else that we can do. Oh, I didn't, yeah, but I saw when I started. So in 1 hour from when I started, I will stop. We spoke about dynamics. So let's start again from dynamics. And see little by little how we end up having probabilities. Now, okay, better. Okay, so we need a few ingredients. One, we need some space, okay, that we call phase space, that is a subset of Rn. Usually it is a manifold, meaning a differentiable manifold, meaning a set which is very, very nice. It doesn't have sharp corners of things, okay, in which points move. So you take an x in M, and then you have a law. The law is x dot equals g of x, where x dot is the time derivative. Okay? Then time could be anything else. It is in an abstract sense. Okay? Then, under proper conditions, for instance, Lipschitz continuity in things, okay, but I cannot go into the theory of differential equations, just take it for good. In a compact differentiable manifold, the solutions exist if the vector field G is also smooth. Okay? This exists globally, so for all times. So we consider we are in this case. Then we will have an operator, phi t, that takes point in M and pushes them to other points in M. Okay? You take 1x here, and after a time t, it will have become phi t x. Okay? Which also belongs to M. Phi t is what gives you the solution of this, in general, system of differential equations, because an operator, linear operator, continuous operator, is called involution, that takes points in M, gives you another point in M, okay, with this property that I apply twice is equal to the identity. Okay? I'll give you an example. Then, if so, time reversal invariance, if there exists an involution, okay, an involution is a unitary operator which has this property. If there is an involution such that the evolution forward in time combined with I, applied to any x, phi t I x, is equal to I phi minus t x. Okay? Why is it called time reversal invariant? So this is for all t, which could be all r or all z, and for every x in M. What does this property tell us? Well, you remember that I squared is equal to 1. So if I apply I on the left, I phi t I x, because this is a point of our space. Then this is a point of our space. So to a point of our space, I can apply I. Okay? I phi t I x is equal to I squared phi t, phi minus t. But then I squared is the identity. So it's equal to phi minus t. So what you have in this case is that if there is one such involution, then you can go backward in time without having to go backward in time. You only go forward in time. You apply I, you go forward in time, you apply I again. Where are you? Where you were in the past. You never went back in time, okay? Don't let be fooled. You will find places where they tell you that you can go backward in time. Not us, okay? Star Trek or the story of the Empire, okay? I don't remember how it is called, okay? There maybe you can go backward in time, not us. But it is true that at the level of elementary particles, and even these days of atoms, they can do little tricks like this. They can do it. In any case, what you're actually doing is going forward in time. And then you have to have a smart operator I, which may be not trivial. And if I want to get younger, I can assure you that I is not easier to find. It's not easy. Okay. I have a picture in my notes that are there. What this should be read is something in this way that says, I have my point x represented by two things, by a point and an arrow. The arrow tells me in which direction I'm moving, and the point, okay, but x is both. X is equal to point, arrow. It's not just the point. So suppose I have a trajectory that does like this. So this is my x. And this will be my phi t x, a time t later, which means I have a new point and a new arrow. If I apply to this, if I apply to this x, I apply I can imagine that it is like reversing the arrow and keeping the point. Okay? So this is x, this will be ix. Now, if I go forward in time, oh, sorry, I wrote it incorrectly. Look, t and minus t are the same. They are just two real numbers. So I can put the minus here and the plus here because it is better. Okay, so I apply I revert the arrow, and then I go backward in time, and I arrive here. I arrive at I phi tx. What is this? This is a point and arrow, that if I now evolve it forward in time, I come back to where I started. So it is a new initial condition that does the trick of going, in quotes, backward in time. Okay? It doesn't really do it, but that is the idea. So many dynamical systems have the property of being invertible. The inverse exists. And some of being also time reversal invariant. That means there also exists an involution with these properties. They can be used, okay? They can be used. For instance, if you have systems in a magnetic field, which is something of interest in plasma physics, for instance. Okay? A magnetic field requires a special eye, but I am the one who has found the eyes that are suitable for magnetic fields. Now, this is about dynamics. Now, what are we interested in? On the dynamics or on certain properties that evolve with the dynamics? What do I mean by this? Okay. The weather here today is a combination of the properties of all the molecules of the air. okay, that move around under the forces that produce the winds, okay, the variations of pressure and so on. So I could try to speak about what the molecules of the air do. But then when I know what the molecules of the air do, I don't know if I have to wear gloves or not. I prefer to speak about temperature. So temperature is not dynamics. Dynamics is what moves the molecules. What is temperature? Temperature is an observable. It is an observable quantity, maybe not with your eyes, but with the thermometer. Okay, its value can be computed. Okay, what is an observable? An observable is a function of the points of your space, or is a function that takes points in M and produces a real number. Okay? So the temperature in particular can take positive and negative values in Celsius, in the scale of Celsius. Okay? In the scale of Kelvin, it can only take positive values. Okay. Just a function like this, we call it observable. Now, what is temperature? You know, I think practically all of you, or perhaps with few exceptions, have never seen the thermometer that you had to stick under your shoulder and keep it for 5 minutes. Sivaraji, are you old enough to have known that thing?
Yes?
Yes?
Yes. Still we use, and the light also they are using. Now they are using 2. Sometimes they keep it, and now they are using lights.
Yeah. Well, in many countries of the world, in the West, the old one has become illegal because the liquid inside, mercury, okay, that is toxic. So you know what happened to me? Because I travel a lot, I went through the security for a plane to catch a flight. I was always carrying this small, okay, that say if I get sick, at least I check if I am or if it is all in my mind. They tried to say, what do you go with this thing? I thought, well, I mean, this doesn't kill anyone. It's not a knife or whatever. No, gone. And that was the last one that we had in our house. So now only the pistol. You can use watch. Okay, so in any case, you know, the characteristic times of the motion of molecules are of the order of 10 to minus 10 seconds, or even shorter. And when you stay 5 minutes like this, it is practically an infinite time for a molecule. Okay? Because 5 minutes, okay, you have 60 times 5, which makes 300, right? 300. 300 seconds, okay, and you have 10 to the 10 events in 1 second. So it is a huge time for a molecule. So what is the temperature that you measure? But even in 1 second, even if it is just 1 second, you have had 10 to the 10 molecular events, and sometimes 10 to the 12, if not 10 to the 14. Okay? What has happened is that you observe an average property of the motion of molecules, because in such a long time, molecules have explored a large amount of different states. And that single number, which is temperature, summarizes all those practically infinitely many states. So mathematically, what do? Mathematically, we define the observed quantity in this way. We say that the observed value is the time average of the observable O along the trajectory that started at a given point x, and that is defined as limit for time that goes to infinity of 1 over time, integral over time of the values that the observable takes along the trajectory, starting at x. Okay? So, phi s x is the point at time s. O is a function defined on M, so it takes a value there. If you integrate, you sum over all the values along the whole trajectory up to time t. Divided by t, you have what is called the time average. Now, we say that the observable is a function of the phase space, as it is called, that produces a real number, and that the observation depends on where you started, okay? Because if you started to average yesterday outside, you get a different number because you started in a different place, okay? Then you make the time very large. Now, of course, in reality there are no infinite times, but I told you, tell me if 10 to the 10 years wouldn't look infinitely many years to you. Okay. You see, in mathematics, we have a problem, because if I write 10 to the 10 to the 10 to the 10, it took me 3 seconds, right? But this number doesn't exist. This has no relation with anything at all that you can find in the world. Okay? And so it is just so easy to draw. Power of the mind. So we would like to say 10 to the 10. But if we don't take the limit, the mathematics becomes very difficult. There are what are called finite size effects. If I don't take this limit, okay, and I do that, I say this is 1000. Very difficult. Very difficult. Not on a computer, however. And so, from when computers are available, finite size effects are being studied more and more. But mathematically, if you have to do calculations, you know what it means taking h goes to 0, and you compute the derivative. You know what it means taking t to infinity. But what it takes, taking t to 1000 is difficult. Okay? You have, because the corrections can be difficult to compute. So anyways, to make the mathematics easy, this is what we do, and most of the times it is a very good approximation. It is not infinity, but it is a very good approximation of reality. The difference between the integral from 0 to 10 to the 10 divided by 10 to the 10 from taking the limit to infinity is not, I mean, you will never notice it. You will never notice the difference, okay? So the mathematics is good. But keep in mind that these days we look at small systems over small times. Okay, I was told that I work with nanotechnologies, for instance. Okay, there we have times this short and also shorter, and so we cannot take the limit to infinity. But that is where we start, and then we will get more. Now, you know, if the dynamics are like those that I drew, I didn't draw, they were on my slides, in the morning, where there are those big fluctuations that you don't know where you go, it means that computing this integral is practically impossible. It is still easier than other things, but it is impossible, because this thing will vary tremendously, and you don't have a way of following these things. Okay? On a computer, you can try to approximate as better as you can but for instance, it would mean you have to use very short time steps, and that it will make it computationally very expensive. And there will still be errors that propagate. So it's a mess. Not impossible, because a lot of progress has been done, but it would be much, much better if you get an average from a probability. Okay? It would be much, much better if you can write that this thing is equal to an expectation value with respect to a probability mu of my observable O, where by this symbol I mean the integral of O of x d mu of x. If I can do this, and if mu is a decent thing, then we are much happier. Okay? Then we are much happier. So here is how probability comes in. If the dynamics is complicated, this calculation is impossible. And it quickly becomes impossible. But maybe it is complicated enough, and better be very complicated, that there is a simple mu that does the trick. You have to be careful, okay, a little bit of probability theory, that these two things cannot be generally strictly equal. There must be some exception. Okay? Because you see, here there is the dependence on x, while here you have integrated over all x, so the dependence on x is gone. So measure, or excluding set of 0 mu measure. Okay? What do we mean by this? Now, let's see if I can use efficiently my fingers. Where did I put this? The cup. No, because then it gets dried. I'm sorry. I'm sorry. It fell. Ah, I made it fall. Okay. Yeah, I apologize. So what do we mean by this kind of language? It is there. But you know, when I went to lunch, I finished lunch, and then I took my jacket, okay, to come back. I was like this. I was saying, okay, where is my phone? Where is my phone? It happens to you? What do we mean by a measure, by mu measure of a set? It means that we... that's the... okay, pen. Yes. Pen. Okay. It means mu of E... It wants to write of its own. I use the other board. I use the other board because I noticed that it writes things when I don't know how not to make it. Then switch it off, Sivaraj. Thank you. I will try it. Thank you. Yeah, see what we can do. So I take a subset of M, my space, okay, and by the measure of the set E, mu of E, I mean the integral over the set E of d mu. Okay? So that equality there of time average and phase space average, as it is called, will be good if the exception is a set of 0 measure. Okay? When do we call it a probability precisely?
Now you can also use this. Yeah, now you are free.
Huh?
Yes. So now you can use.
Okay, so now first I fill this one, and then that I know how to remove. Select.
Yes. Delete. Yes.
Huh? Okay, we call these integrals a probability if we have this property that 0 is less or equal than mu of e, less or equal than 1. Okay? I should say for every e subset of M, not any e, not any subset really, but for every e that belongs to an object that is called the sigma algebra defined on M. Okay? A sigma algebra is written in my notes, but just tell you quickly in words, is a collection of subsets. That is not all the subsets of M, because that leads to paradoxes. Okay? If some of you are familiar with Banach-Tarski, paradox, for instance. Okay? So you cannot give the probability of all subsets of M if M is a continuous set. Okay? Because the property of continuum is beautiful and terrible at the same time. Okay? But you have to choose a certain collection of subsets, in particular a collection that is closed under unions and complement, up to infinite unions. Okay? Topology is less strict. So for all so you choose your collection, you choose it. You choose it on the grounds of the applications you want to consider. Okay? Then, for these sets, if you have this, you can speak of a probability adding that mu of the whole space has to be equal to 1. Okay? That mu of the empty set has to be equal to 0. A subalgebra, a sigma algebra always contains the empty set. Okay? And then you have to have this property. Mu of E1 union E2, if they both are in the sigma algebra, equal to mu of E1 plus mu of E2 minus mu of the intersection. Okay? This can be a very general notion, but you can think of it as volumes, okay? As volumes or areas of sets. Say this is my M, okay? I give it probability 1. Then what is the area of E1 union E2? In this case, the intersection is 0, and then you get the sum of the two. But if there is an intersection, okay, then if you take the sum of the two, you count this twice. So you have to remove it once. Okay? Now this makes a probability. Sets, subsets in the phase space can be associated with functions. Okay? In particular, with what the probabilists call indicator function and the analysts call the characteristic function of a set E, always in the sigma algebra, of X. And this function is defined how? It's defined as 1 if X belongs to E and 0 if not. Okay? Then this integral up here can be reduced always to an integral over the whole space, because then mu of E is equal to the integral over the whole space of chi E of X d mu of X. Okay? This connection between sets and functions is very important. because sometimes it is easier to work with sets, and sometimes it is easier to work with functions. But these characteristic functions have a very good property, that linear combinations of functions like this are dense in the space L1 of M and mu. Okay, they are dense. They are called simple functions. Okay, you can write them this way. Now I can use the one in the middle. And the cap is here. So, there is a pen? This one. No, you said that. Okay. Well, if there is this, it's better than if I use my finger. I think, we will see. You tell me if it is readable. What was I saying? Okay. Simple functions are functions of this form. I have to be careful, huh? The color. Black. Or blue even.
Yes, and if you want in here, I can make. Okay, this is recognition. Try plus. Yes.
Okay, let's try again. Now, that goes away. That go. Okay. Let's see.
Yes.
No.
In hands.
But let's make with hands. With hands. Okay. So. Okay. Now I know. Delete.
Yes.
Delete.
Yes.
Okay. So F pen. F simple of x equals to sum in k from 1, maybe it is a bit too thick, from 1 to n of complex coefficients psi k Okay, these are simple functions. Okay, the coefficients can be complex numbers. Okay, these functions, the set of all these functions is dense in the L1 functions, which are the ones I want to make it less thick. Okay. Sorry?
It's multi. If you make it pen, maybe now it may go with the same color.
Yeah, it doesn't matter. It doesn't matter. It's okay.
Yes.
It's okay. Because I don't want to keep people too long. Somehow it likes that one. No. Never mind. No, it doesn't matter. Okay. I just use my finger. Sometimes electronic devices are a bit disappointing, but typically the fault is ours. Yes. But I cannot blame Sivaraji because he did his best and I couldn't do any better. So if you take the set of all these ones, okay, they are dense in L1. It means that you can approximate every L1 function, which is more than you need. L1 functions are really too many. Okay. A function is in L1. F belongs to L1 of m mu if integral absolute value f of x the mu x, okay, is a finite number. Maybe you can do better. Yeah, it's okay. maybe if you select.
Oh, we black कर दिया.
No, I got very small. You see, yeah. In the meantime, I continue with this. But you have seen, okay? They are standard definitions. Okay. So coming to this other side. No, but we had found a pretty useful equilibrium. So if we can go back to what it was, I can use it. It was fine, you know, it was fine. Okay. Yeah, that's very good. Yeah. Ah. Ah. I see. Okay. Ah, nice. Yeah. I can move it. Okay. Okay, so let's put it this. Okay. Now, erase that. Okay.
Maximize, you can use like this.
Yeah. Okay.
Minimize, and if you wanted to move, we'll just touch it.
Yeah. Okay, perfect. Thank you very much. What you can do are two equivalent things. One is you choose the sigma algebra. You choose which sets you want to which sets you want to attribute a probability. Or you choose a function space. You decide which are the functions of which you want to compute averages. Okay? Because now with these tools, well, it was on the board before, but okay, you remember that? Is it here? No. That I had the expectation of a certain function f as the integral over m. It was O, you're right, but okay, it is the same thing. Okay? So if you choose a different sigma algebra, you are telling me that you want a different set of functions, because you can build your functions from simple functions that are taken from the sigma algebra. Or if you choose a set of functions, it corresponds to a certain choice of sigma algebra. And there are sigma algebras that are larger, they have more sets, they imply you can make measurements, finer measurements, or there are fewer sets, which means you measure more coarsely. Analogously, you can have a bigger space, L1 is a very big space, or you can have a smaller space. For instance, the analytic functions, it is much less than L1. Okay? And still, analytic functions, from one point of view, are not good enough, because you like to have discontinuities, for instance. But from other points of view, even they are too many. Okay? Connecting the mathematics and the physics here is a bit tricky. Okay? Because, for instance, physicists will be happy with 5, 6, 10 observables. Any function space has got infinitely many. Okay? So you have to be careful. It's a little bit like the integral from 0 to 1000. Okay, or from 0 to infinity. The mathematics wants to go to infinity, and the physics would stop at 1000. Often, they are indistinguishable, but sometimes they are, so you have to know. Okay, Now, you have, what do you do with the probability? You compute expectation values or averages. They are called expectations because it's what you expect. Okay? But often, an average is what you expect. In the case of the temperature, okay, what we believe is that what you observe is an average, but is also what you expect. Okay? So you use this kind of language. Choosing the functions is equivalent to choosing their expected values. So you can also decide to choose the expected values. Okay, like, well, I just said. Now, the question is, but if we have a dynamical system, the points that are in E will be moved by the dynamics to other points. Okay? So you will have that, say, this is your set E inside the big phase space. Okay? And now you let time pass. And this point goes here. And this other point goes here. And this other point goes here. And so you have a new set. Okay? This set here will be, if it was an evolution for a time t, phi t e. Okay? What does that mean? It means that if I had some probability given to E through my measure, probability measure mu, this probability now is here. This is an assumption. Okay, we assume the points carry with themselves their probability, not points, sets, carry their probability with themselves where they go, under the dynamics. It is like thinking of a fluid that carries its mass as it moves. Okay? If, say, I take this glass, and in fact, I need it. So you see, the water that was here, now is in my belly. The mass that was here, now is here. Same thing with probability. Now, I need more. Now, remember that if I throw this to you, you get wet. If I throw you a probability, you don't get wet. Yes. Okay? It doesn't touch you. So this is what is called an anthropomorphism. Okay? Is our way of looking at things. We are used about material objects, and also the abstract objects of mathematics, we want to think that they are material. Perfectly fine, but remember, a stone hits you, hurts you, a probability doesn't. Okay? Water makes you wet, and in cold weather you don't like. A probability doesn't make you wet. But we want to use the same. We want to use the same. If we are lucky, this thing will produce something useful. And if we are not lucky, we'll have to change. Maybe I can go another 10 minutes. So, no, I think that if I take 10 minutes more, I will not be left much behind with what I had. So if you receive, because I started 50 minutes ago. So for 1 hour is another 10 minutes. Okay, and then we'll see, in case I take a bit of the tutorial. So, with this idea, we can define the evolution of a probability. Okay, we define the evolution of a probability. How do we define it? We define it this way. In the first place, we introduce the pre-image of a set, phi minus Te, okay, which is all the points in the phase space such that their evolution is in E. Okay, so they are all points, phi minus T are all the points that if you give them a time t, they will end up inside E. That's why it's called pre-image. Okay, you can do the pre-image of the logistic map. You have the parabola, and now you want the pre-image of this set E. Okay, it is the union of two sets. This one and this one. Okay, this and this are the pre-image of this. Because if you go from these points, you end up inside E. Okay? And because the parabola is not monotonic, then you have two sets that will join forces to produce E. Okay? So, first you introduce the notion of pre-image, and then the evolved probability is defined in this way. We have a new probability, new, because things have changed, of a set E, still a bit too thick.
Use the pen for doing that change. Because that was the thing I did not do.
It goes from 1 to 5. Maybe 1 is too. Let's see. Nu of E.
So you use a different marker?
It doesn't matter. Okay, it is okay. Okay, it becomes the integral over the set E of a new probability d nu equal to the old probability in the pre-image, which is the integral over the set phi minus Te of d mu. It is this idea. Okay? Now, if I call this E, eraser.
Yeah. Click in the pen and use your
Right. Okay, if I say that this is the set E, then this is the pre-image. Okay? If this is E, then this is phi minus Te, because the points that are inside here came from here. Okay, so what I've written there is, in E, I will have the probability that the time earlier was in the pre-image. And this way, I define a new probability. Okay? Yeah, I still have 4 minutes. So, if we want it in terms of the sets, this is equivalent to tell, say, if I say that this change has taken place in time, then I could say that I had an initial probability μ0 and another probability at time t. and I will define the evolution up to time t of the probability exactly as I have. I will write mu t of E equals integral over E of d mu t equal to mu 0 of the pre-image, which is the integral over the pre-image phi minus t e of d mu 0. Okay? So you see now from the dynamics that moves the points, I have obtained the evolution of probabilities. So probabilities can change in time. So for instance, say the probability of some event today is something, the probability of the same event tomorrow could be something different for a whole bunch of reasons. For instance, think of a medical test or some medical operation. Okay, if I have been under surgery today, and luckily I have to have surgery again tomorrow, the probability that something goes wrong is higher. Probability is not the same. Probability changes in time. This is one mathematical rule to, if you know the dynamics, to decide how probability will change. Still keeping in mind that probability is not a stone. Okay? And this, and with this I finish this hour, and this has a consequence for the observables, because then the expected values of the observables will change in time. Okay? Because we will define, where is it? Mixing up my notes. I'll just go by heart. Okay, it doesn't matter. Okay, we will define the expectation at time t of my observable O as, now you can guess what, as the integral over all space M of the observable O of x integrated with respect to the probability at time t. Okay? Which in general can be different from the expectation at time 0 of the same observable. Okay? Temperature at time t and temperature at time 0 should be defined as the integral over m of the observable is the same, but the observed value is different because d mu 0 of x may be different by d mu. Okay? There are situations in which things don't change. Okay? If mu phi minus t e equals mu of e for every e in the sigma algebra and for every time, we call this mu an invariant. Probability. And what does it produce? It produces that expected values don't change. E at time t of O will be equal to E at time 0 of O for every t. And for every O in the function space that corresponds to the sigma algebra or the function space that you have chosen. Okay? So we have, like for points, for the points that move, we had the fixed points, we have the invariant probabilities. The invariant probabilities are fixed points of the evolution of the probability. Okay? Now, this is a bit abstract. In the tutorial, we see how to do some things with this in simple cases. Okay? All happy? All happy. Thank you, sir. Thank you. Thank you for your patience. for bearing with me. Yeah, questions? Now you find this in my set, it is a chapter of a book that I'm writing that is called Probability Something. It is in the folder.
Share the complete folder with all the participants?
You can share the folder with whoever you like, yes. Yes, I'll be glad that people use it, yes. Yes. When do we reconvene?
3:46, then we start with 4 o'clock.
4 o'clock, perfect, perfect. In the lab. Okay, so we move our stuff from here. Yeah, okay.
So you please take tea and biscuits, and then we will again disassemble the lab. That is with 4 o'clock. This is the lab, PG computing lab. Just one thing off. This, okay, please arrange it. First you arrange it.
Yeah, I switch this off.